Okay, in this podcast we're going to take a look at strong and weak acids and bases. Now, it's easy to confuse the term strong and weak with dilute and concentrated. So if I have a dilute versus a concentrated acid, you're talking about something, like whether or not I have a 1 molar or a 0.001 molar or a 10 molar. These tell me whether it's dilute or concentrated. So any acid can be strong or dilute, right? But an acid is either a weak acid or a strong acid. It can't be both, okay? So the difference then is a strong versus weak acid. Let's take a look at an animation and we'll talk about the definition. So you can have a concentrated acid that's strong or weak, or a dilute acid that's strong or weak. Okay? So strong or weak don't refer to concentration. It's coming.
This animation demonstrates the difference between a strong acid, hydrochloric acid, and a weak acid, hydrofluoric acid. Click on one of the buttons to see hydrochloric acid, HCl, or hydrofluoric acid, HF, dissolved in water. Hydrochloric acid is a strong acid. Strong acids are strong electrolytes, which for most purposes are assumed to ionize completely in water. In this case, HCl ionizes completely to hydrogen ions, H+, and chloride ions better represent like hydrochloric acid donating an H+ to water, producing hydronium ion H3O+, and chloride ion. The role of water in this reaction was not shown to simplify the animation. You can think of H+ as a shorthand representation of H3O+.
Let's look at hydrofluoric.
Hydrofluoric acid is a weak acid. Weak acids are weak electrolytes, which only ionize to a limited extent in water. At equilibrium, a hydrofluoric acid solution contains mostly non-ionized acid molecules, HF, and a small amount of hydrogen ions, H+, and the conjugate base ions, F-. This reaction is better represented as hydrofluoric acid donating a proton to water, producing hydronium H3O+, and a fluoride ion. Remember that weak acids only partially ionize in water. The role of water in this reaction was not shown to simplify the animation. You can think of H+ as a shorthand representation of H3O+.
Okay, so here we have a weak acid, which means that the hydrofluoric does not ionize very much. Most of it remains HF, and it doesn't break apart into H+ and F+, as opposed to the hydrochloric, where it completely came apart, almost 100% ionization. So that's the difference between strong and weak. Let's go back to the notes on that. Alright, so the strength of an acid or base is determined by the amount of ionization, and usually it's either going to be almost 100% or very little, like 10%. Okay? So hydrochloric is strong. It will ionize 100%, which means it comes apart. The H+ and the Cl break apart. You end up with the chlorine minus in the hydronium ion. It 100% ionizes. So there's no real way to easily explain at this level what causes an acid to be strong or weak, but there are a list that we can give you that tell you which ones are. So these are the list of the only strong acids. And the ones that we usually refer to, and that you should know, these are HCl, hydrochloric acid, HNO3, nitric acid, and H2SO4, sulfuric. So memorize those three, but there are a few others. So weak acid are much less than 100% ionized in water, usually down 10% or less. One of the best known acids that is weak is acetic acid, and the acetic acid will ionize to form the acetate ion and the hydronium, but most of it does not. And this is a two-headed arrow indicating that the reaction goes back and forth. So you end up with mostly acetic acid in there. So just like a strong acid, a strong base, 100% ionizes or dissociates, and it's synonym for ionizes, in water. So sodium hydroxide breaks apart completely to sodium plus and hydroxide minus. Other common strong bases, again, are basically the bases of the alkali metals in group 1 and the bases of alkaline earth metals in group 2. So that's what you need to know. Alright, so a weak base, less than 100% ionizes in water. One of the most common known is ammonia, NH3. So we have NH3. It picks up a hydrogen ion, a proton, so it's a base. Okay, so now we're going to talk about conjugate acid-base pairs. So let's say I have an acid, and this acid is in water, and the acid will lose its hydrogen plus and become, in the process, just the carbonate ion here. Now when it does that, it is now available to pick up an H plus, so it's going to act as a base. Two-headed arrow, this goes back and forth. So I have an acid, but the acid, once it loses its hydrogen, becomes a base. So we call this a conjugate base. So this is the acid and its conjugate base pair. So water here picks up a hydrogen ion or a proton, so it is acting as a base here. But once it picks up that proton, it is now available to donate, right? So here it's a base. When it loses that, picks up that H plus, it becomes the acid. It's available to lose a proton. So let's take a look at what we have here. So we want to look at what has lost a hydrogen as we go from left to right. So what we have here is H2PO4 minus. So what's happened is that's gone from H2 to H, so it has lost a proton, so it's acting as an acid. But once it's here, it becomes a base because it's available to pick that H plus up again. And here we have the carbonate ion, and it accepts a proton, so it is acting as the base here. But once it's here and it has the H plus attached to it, it can now donate that H plus. And again, you see this double-headed arrow, which means these reactions go back and forth. Here we have H2O and SO3. So it looks like the H2O is what's losing the H plus, so it is acting as the acid here, and the conjugate base is going to be the hydroxide, so it's a base now available to pick up an H plus. And the SO3 is accepting an H plus as it goes over here, and now that it's accepted the H plus, it can donate it, so it becomes the conjugate acid on this side. So this is a base and it's conjugate acid. Alright, so see if you can identify what the conjugate acid and base pairs are, and then I'll go over them. So go ahead and pause it. Okay, so if I look at this again, I've got an H2 here and an H here, which means this is acting as the acid. Once it loses its H, it becomes its conjugate base. NH3 picks up the H plus to become the ammonium ion, so this is acting as a base. Once it gets here, though, it's now acting as an acid because it can donate the H plus and become an H3. Alright, so here we have water. It is donating an H plus, so it's acting as an acid here, and this becomes its conjugate base. And we have HS. It is picking up the hydrogen, so it is acting as a base here. And now that it has the H picked up, it's a conjugate acid because it's available to lose the H plus. Alright, so let's just take a look at these two. See if you can answer these and then unpause and come on back. So I have HCl. Clearly it loses an H plus, so it acts as an acid here. The OH picks up an H+, so it's acting as the base. So this acid has a conjugate base. This base has a conjugate acid. Here, the H that's the compound that's lost the H is sulfuric acid here, H2SO4. So here it is acting as an acid. This becomes its conjugate base. Water is picking up that H+, so it's acting as the base, and it becomes the conjugate acid here. Now, one of the interesting things here is you have seen that water can act as both an acid and a base, and we call that an amphoteric substance. Amphoteric means the substance that can act as an acid or a base, and that's a term you need to know. Okay. Alright, so we're going to stop right there.